the roller. Actually, permeance function is developed when they studied the induction motor, the current, the roller bar, the current flowing, and at that time, there's also the current slot in the slot, but previously they are interested in the flux path, the distribution in the air gap. So probably you can think the flux will be it's concentrated like this. They want to know the exact or accurate distribution in the air gap of the flux density. So, alternatively, they imagine or developed a calculation method like this. Electrostatic, it is developed by electrostatic problem. For example, here, the core or the conductor. This is conductor. And here, the voltage is assigned 0 volt. And here, this surface or everywhere. It is very important to learn to study the engineering mathematics, not mathematics. 네. 왜? 아빠 지금 세미나 하는데? 세미나 왜? 얘기해. 뭐 간단한 얘기. 아, 그래? 아, 그래? 아, 그럼 밑에서 공사하고 있는지도 몰라. 어쩌면. 아, 그래? 아, 또 오늘 뭐 온다고 하니까 어쩔 수 없지. 그렇구나. 그래야. 아, 또 불쌍해. 그래야. 알았어. 지금 세미나 하고 있어. So this surface has potential 0 volt. This surface 100 volt. In this case, we can ask ourselves a question to ourselves: can we calculate electric field in this problem? So it is possible. True. So numerically or mathematically, it is possible. If the geometry is not complicated, but it's very complicated, so it is almost impossible. But mapping. Have you heard about the mapping or the mirror method? Have you heard about the mirror method? Whatever. 이걸 뭐라 그러지? Image method. Image method. So many people research to study this problem, the image method or the mapping method, so they can draw the flux distribution like this. and then it is quite complicated distribution, the flux, the path, and then someone define the specific permeance. It is function of P theta, means just actually just length, the path length. How long this path, 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 how long. It is definition of specific permeance actually. So P0 plus or minus P, approximately just one P1 cosine something. And this function shows the length of flux path, just the length. But, so what does it mean? Length here, length here, length here, length here, length longer, length longer, length longer, longer. And then some MMF will be applied to this area. We can get the flux density by using the length of the permeance. And one more thing. The permeance is given by this function approximately, and when you apply a current here, positive and negative, and its number of conductors is n. For example, if this is air gap, in this case, the permeance is infinite. We can calculate flux density by using this function, and we know the MMF here because there is conductors, current carrying conductors. Yes. So MMF is exact because some area you can apply H field is Ni. So and then apply here H field is 0, here H field is not 0. So MMF is applied to this area and this area. So it is just given by the flux density is we have if we use this function P function and H function gives flux density. So we use MMF F product P gives flux density. It is right, probably quite similar or quite exact. But in this case, in our problem, it is also approximate. There's a magnet here. Magnet. We have to simplify this structure to calculate analytically. Actually, MMF alternatively we can magnetization function, the vector is of everywhere some direction of magnetization, but we simplify just current carrying conductor. And gap, this magnet is replaced by current carrying conductor like this, and then its current is given by some equation, and then this magnet is replaced by this current. So it shows it represents exactly the same phenomena. It's different. It should be different because it cannot be this one. In lumped primer, it is possible. For example, magnet here. This one is plus minus and reluctance one, and it has some value of BR and GM magnet thickness and some value and magnet reluctance. This structure can be replaced by this equivalent circuit, but in this situation it should be different because I mean actually exactly it should be replaced by this one, the current, the surface current. If the magnet is replaced by this current surface, the surface current density, it is exactly, it is right. It would be right. But this one is simplified, just current carrying conductor, single current carrying conductor. So in this area, the flux density value, it should be different. It should be approximate. So everything we are solving is just approximate solution. So it should be different. So there are so many ways to calculate exact solution, but it should be it would be very complicated and it is hard working. So but if you're interested in that method, you can study it. Almost everything is published in paper, especially Professor Ju, the Sheffield, the University of Sheffield. He is very strong in this calculation. The solution, solving the differential equation, the second order, the consider the geometry, very complicated geometry. They solve the second order differential equation. So and then they calculate the exact flux density distribution in real geometry. But the solution is also very complicated, so it is very hard to apply, to use the numerical, the machine design. So we use very simple method like this, but it must have some error. You have to understand the procedure. But everything is worth studying. And few questions. By FEM, using FEM, can we get this function? I think it is almost impossible because we have to calculate the flux density way the real waveform, and then you have to calculate the length of the flux length, path length. So it is quite hard and very complicated, or almost impossible, or not useful. So if you, when we change the geometry, if you have to calculate the permeance again, it is no use, right? If it provides some general calculation result, it would be useful, but I think it is quite hard.